Oh, well, there's J.K. Rowling's on Twitter. She's actually quite entertaining if you are potentially ever get Twitter because you guys are young and whatnot. J.K. Rowling's has done things. There was, what did I see? Some nurse had a grocery store cancel an online order in the UK on this poor lady. She was a single mother working like 12-hour days and all this stuff, and the grocery store canceled her order. So, and this person randomly took to Twitter. J.K. Rowling's found it, contacted the grocery store, made sure it got redone, and paid for this poor lady's groceries. And it's like she does all these random things. She's a wonderful woman and wrote a really good series of books. So yesterday we started chapter 15. We shouldn't take too long today. We talked a little bit about water being strange because of these hydrogen bonds that are really strong, things that are in a similar row, even if you go down below it on the periodic table. Um, H2S, normally the heavier things get, the more likely they are to be liquids or solids or whatnot. Well, H2S is significantly heavier than water. H2S behaves more like the rest of those than water. Water is just like the perfect kind of thing. We talked about solutions, solute, solvent. Is air a solution? Maybe. Like dissolves like. Will it dissolve in oil? Will it dissolve in water? Or if you put certain oils in the fridge, they kind of solidify. Why salts dissolve? Because the water molecules surround each ion and effectively rip them off of a crystal. Some things aren't soluble because the interaction between the positive and negative is so strong that you can't break that. Things that are polar, which are things that normally have OHs, technically ammonia will dissolve in water because it's polar. Any polar molecule from chapter 8 will generally dissolve in water to some extent. So electrolytes and what happens in solution. We talked about net ionic equations a little bit in, I don't know, chapter 11. Um, if you get an ionic compound to dissolve, you get what's called an electrolyte. An electrolyte is a substance that conducts electricity either when you melt it, LT melted, or dissolved. If you melt it, you get basically a sea of ions. You get a whole bunch of positives and negatives. But ionic compounds typically have really high melting points, so that's not exactly an easy thing to do. There's actually a whole subfield of inorganic chemistry called ionic liquids, and they're actually really neat. I don't know what temperatures you need, but they are kind of nifty. But generally, if you dissolve salt in water, you get a whole bunch of sodium ions. They float around. If we think about amounts, like the amount of solute is so much lower than the amount of water. So you have all of these things bouncing around, and because this chlorine is free to move from one side to the other and the sodium the same, you can have a movement of charge. Charged pieces normally ions, but technically electrons. When you pass a current through water, it's not really electrons moving, it's ions moving, and you add electrons to some. And ionic compounds and strong acids are electrolytes because if you take a pile of salt from your cupboard, throw it in water, you get a whole bunch of sodium ions and a whole bunch of chloride ions. And depending on the solubilities, some are stronger, some are weaker. We can test this. You can put meters in. There's the there's a really simple apparatus that you can build with like a D battery, a couple wires, and a little batter or a light. Because once you dip the two leads into the water, it completes the circuit and the light will turn on. We have some of those at school. However, I don't have one in my basement, so I don't really know. So an electrolyte is something that conducts electricity. We talk about electrolytes like Gatorade and Powerade and all of those. Those are called electrolytes because they have sodium and potassium and other ions in them that when you sweat, you're sweating out salt. I'm sure you all have licked like a sweaty arm, preferably your own. And it tastes salty because you're losing salt. And Gatorade was actually developed at the University of Florida, whose sports teams are called the Gators, uh, as a way to get electrolytes back into your system. Water is important, but you also need some electrolytes, sugars. Non-electrolytes are things that do not conduct electricity. You dissolve a bucket of sugar or salt in water, you get an electrolyte. It will conduct. You do the exact same thing with sugar, nothing. You can dissolve them, but because they don't produce ions, they don't conduct electricity. Electrolytes, non-electrolytes, and weak electrolytes. Um, these are generally things that have low solubility or a small amount dissociated. Um, examples of like low solubility is the low solubility chart you're going to run into if you take chemistry 12. You are going to run into the term weak acid. A weak acid is an acid that doesn't split into ions completely. There's strong acids like hydrochloric acid, hydrobromic, hydriodic, nitric, sulfuric, and perchloric. Those six go 100% to H plus and Cl minus. And they do this. Acetic acid goes to acetate and H plus, but this only goes like it's less than 1% that it ionizes. So you have a significantly smaller amount of ions. They'll still conduct, it'll still kind of complete that circuit a little bit, and you'll get a little bit of a weak light signal, not symbol. Um, so these things, they generally don't make ions when they melt. So the idea with these is write a dissociation reaction for the following, if possible. Check solubility. So I need my solubility chart. And I'm just going to do a few of these because I'll do a select few. So the first one was potassium sulfate. Sulfate. Potassium is not there. So oh, shoot. Potassium phosphate. Phosphate. Oh, potassium with phosphate is soluble. So this one is going to break down into 3 potassium ions. This one, ammonium sulfite, that's going to dissolve. Silver sulfate. Sulfate, most silver. So if we have one that doesn't dissociate, you can say, or you can say AGSO, AGSO, for as a solid. I'm pretty sure barium hydroxide, barium hydroxide does. So this is just another application of why we need to know whether things are soluble. That one will. Zinc chloride, I can't remember, I think it does. Chloride, yeah, that one would. That one will for sure. Methane gas is not ionic. It will not dissolve. It will not dissociate. Glucose or fructose or whatever 6-carbon sugar. Now this one is interesting. If I was smarter than I am, I would have looked up the structure of glucose. My old friend Wikipedia. So Paul Patton. So that's a couple different versions. That's more physical reality. That's kind of looking at it. Glucose has these OHs. There's 5 of them. Because it has that OH group, that is a good indication that something is going to be soluble, but none of those split into ions. So glucose will dissolve, which is good because if it didn't, we would have some issues. But it doesn't dissociate. So we can do something like that. Say, if I take glucose and throw it in water, it's going to stir it up and you can get it to disappear. Sucrose is the sugar, is white sugar. Same idea, which if sucrose didn't dissolve, you wouldn't have Kool-Aid or pop or all of those beverages that, mm, based on who's here, probably don't drink a whole pile of. Oh, I don't know. Maybe Matt drinks all sorts of pop. You never know. But then you get Diet Pop, which has sucralose, which has aspartame and sucralose, which have nothing to do with DDT. Don't believe things you see on the internet. So this is kind of, we could do a little bit of a mini experiment. Litmus paper, you've all seen before, normally in Science 9 or 10 or biology, which tells you whether or not you have an acidic or basic solution. So if you have litmus paper that's blue and it changes to red, that indicates that the solution is acidic. Red turns to blue, means basic. If it doesn't change, so normally what you have to do is dip something, dip a piece of red in, then dip a piece of blue in. And if they don't, if only one changes, well, that tells you one thing. So this is kind of a little kind of identification thing where we could have solutions and we could test them. So we have glucose, which is that will dissolve, but it is not ionic. Calcium hydroxide, calcium chloride, and citric acid. And then we have run kind of 4 tests. We tested the litmus for all of them, and we tested conductivity. Of these 4, acids, bases, and ionic compounds, like it's a process of elimination. We know different things about different properties. The one that I can look at myself, I mean, there's a couple of different ways we can go right from A, B, C, and D. So A is glucose. Will this dissolve? Yes, it will dissolve. Will it conduct? It shouldn't. Is it an acid or base? That wouldn't change litmus. So this one is, because it's not going to change litmus because there's no H plus or OH that comes off. It doesn't conduct because it's a molecular compound, but it will dissolve, and I guess that's somewhat redundant because all 4 of those will dissolve. Calcium hydroxide one of the things that I kind of gloss over, which is a bit of a problem in this, anything that generally it's an ionic hydroxide means this is a base. Bases turn litmus blue and they conduct. So that one's going to be calcium hydroxide. Calcium chloride, it will dissolve, so it will conduct, but there's no H or OH, so this is not going to change litmus. So this one is calcium chloride, and by process of elimination, this one should be citric acid. That will conduct. The only one here that doesn't conduct is glucose. Because this is an acid, this is going to turn litmus red. So that's the only one that turns litmus red. Anybody have orange juice this morning? Because if you did, you had a whole bunch of that. Um, that gives citrus fruit their sour flavor, which is hence citrus, citric. I don't know which one came for. I assume citric acid was called citric acid before fruit, but and that's a properties of compounds. It's I think Mrs. Parley does a full lab with a whole bunch of things. I try to simplify that a little bit. And then this one we'll go through. Um, it's about entities in solution. It's what's there. So it's about, is it an element? Is it molecular, polar or nonpolar? Is it ionic? What should it do to litmus? What should its conductivity be? If you dissolve it in water, what should be there? So iron is a solid. Is iron an element or a compound? Well, this is an element. If you put a piece of iron in water, it would not change that. If it's a solid piece of iron, and there's no entities in solution, I could say iron as a solid. Barium hydroxide, metal and a polyatomic ion. It's got an OH, so this is also a base. If it's a base, it's going to turn litmus blue. Barium hydroxide conducts. So if you have this yes part, barium 2 plus, and so in solution we have barium ions and hydroxide ions. Sodium bromide is ionic and neutral. No change. Conductivity, yes. And I know that one dissolves. I've got to think about calcium phosphate. Phosphate, these ones will dissolve. Hydrogen, sodium, potassium, ammonium. Most won't. So this is ionic and neutral. It's not going to change litmus because it's not an acid or base. No or poor. So if you throw this in water, it sits there. If you take a bunch of it, it's just going to fall to the bottom. This is acid, so this is an acid. Molecular. Technically, this is a, well, This is where that whole thing is. This is going to turn litmus red. This is going to be a poor conductor. This is the one that I talked about. It's a weak acid. You get a little tiny bit of now. If you've ever drank vinegar, I don't know if you're actually it's the ions or the acetic acid on its own or whatnot, but it has flavor. Oh, there we go. Change color for fun. HF is an acid. It's a very dangerous one. It's going to turn litmus red. HF is not a strong acid. It's going to be a poor conductor. The same idea as that one. A little bit. There's a whole chapter in Chemistry 12 on acid-base chemistry. It's that important that there's a whole chapter. This is carbonic acid. Technically, that's an acid as well. Red, poor. This is sugar. This is molecular and polar. No change. No. You can get that in solution. This is ethanol. Molecular, polar, no change. No, but ethanol dissolves in water. Uh, Hypochlorous acid. Well, that's an acid. So this is going to turn litmus red. Poor, but technically yes. And that's just a habit. I started writing hypochlorite as OCl. Oh, a random Twitter follower with a name and a bunch of numbers. You are a bot. OH is a base, is going to turn litmus blue. This would conduct. So, yeah, that's the end of chapter 5 or 15. It's about water. What can we do in water? Chapter 16, we're going to look at quantities. If I dissolve this many grams of salt in water, what is the concentration? And we're going to talk about units of concentration in terms of the real world quickly because it's fairly straightforward, and in terms of chemistry. Um, and that's all for this one. Is there any questions? Oh, Ryan hangs up right away as soon as I'm done. No small talk. Everybody else good? Hopefully it doesn't get too hot in Sussex. Well, I guess it's tomorrow that's supposed to be really bad. Hopefully it stays cool-ish. I don't like 30 degrees. 20 is okay. I can deal with 20, not 30. If you guys don't have any questions, I'm good. We'll see. Well, a handful of you in half an hour.
Have fun in the muggy weather.
I'll try. You're welcome. See you in a bit.